Hello there, my name is Matthew Blom, and I am dealing with my design virtual body mapping, creating a 3D anatomical representation by utilizing standard medical technology with innovative protein design. Our setup, surgical training is complex from the anatomical perspective. Current imaging techniques are useful, however limited on a gram 3D scale of the body. X-ray, MRI, CT scan, radionuclide scan, you've seen this before, but this imaging hardware is expensive. We need to utilize existing equipment. How can we gather new data by using old technology? Will it be safe? Will it be used? Little background is that X-ray CT components are all standard in standard hospital. Basically, X-ray, we know what that is, but CT, it takes an angled out multiple X-ray view to produce a 3D representation. We need to keep this equipment, update the information. Basically, X-rays, how they work is that they are absorbed by denser materials such as bone or metallic components, which can show on a scan. Proteins can bind to cell surfaces as well with specific elements. Maybe we can engineer these proteins to hold dense materials for absorption. If we can capture the binding proteins, we can map this data, and then we can put it into a CT scan to see a 3D model. Protein design, basically what we're looking at is cell membranes are containing a phospholipid bilayer with a hydrophilic exterior. This head can also be attracted to positively charged molecules such as calcium. Iron, a metallic component, can switch between two states, a ferric state, which produces rust when it comes into water. In order to protect this in the body, ferritin, the protein, transports the ion through the body in a closed state. Hemoglobin as well can bind to calcium, which also will turn an affinity to the phospholipid bilayer. If we can find a protein that can connect these two proteins together, then maybe we could have attached to various cell surfaces, and this would increase the iron count totally throughout a cavity, and then it's create a greater visual on. So our protein model looks like this below. As we can clearly see, we have the hemoglobin with the binding protein above, calcium components below, and the ferritin molecules above. And we can paint this along the entirety of a cavity line. To use this, to pump this into a system, we have a standard pump here with 2 injection ports, as well as a pump reservoir that we can pump this protein and the plasma along with it into a body. Design criteria is pretty standard. Accurate haptic feedback or perceived sensation in virtual ER, cost-effective materials, less obstructive hardware that should not leave a big footprint. We need to aim, most importantly, to use existing computer hardware. Here's our results for our self-graded evaluation matrix and the finality on the last page. Basically, this results leans toward using existing computer hardware. This makes sense. Value of hardware and cost effectiveness over all our attributes for a third world country. Haptic feedback, while not really important in this situation, it is important for virtual reality, but we don't have any perceived sensation. A figure over here to the right is a somewhat depiction for possible imaging. This is innovative due to the anatomical correctness and expansive dimension of the scans, where we can put this information of the X-rays into a CT to get a 3D picture. This would help surgical training, but coding the membranes of the living patient may produce difficulties. Cadaver labs would be instrumental in this, but surgery may be difficult to use this. We have to, some limitations are engineering proteins to attach to both the cell wall and ferritin, but not impossible due to current genetic progress. Removing said proteins may be difficult as well if we want to recycle. And this is just all create a better 3D model and a cost-effective measure in third world countries currently for surgical technology and information.